So I'm going to talk about a scalable verification solution for blockchains. This is joint work with Christian Reitwiesner, Sami Michaela, and Robbie Ben Farzad Segedi, and of course all of our open source software contributors, and we're grateful to everyone who's given us advice on this project over the last few years. So, I'd like to start off by comparing two sort of ideas that should be familiar. One is big data on the other hand, and blockchain on the other hand. So when you think of big data, you're thinking like your Facebook, your Google, your Amazon EC2. So when you hear these, what comes to mind? You think storage, you have a place to store data, you have a way to perform computations on the data, and you have some sort of privacy that sort of gives you hierarchical access, as this person can access this and this other person. Everybody has access to different things. That's what makes Facebook go, right? So blockchain, on the other hand, what do we have? Storage, we don't really have storage. We're really pressed for space, right? I mean, your Bitcoin blockchain might be 100 gigabytes, but you're not storing JPEGs and videos up there. Computation, we don't really have computation yet either. I mean, you have smart contracts, but this is they're pretty limited bandwidth. So this is where TrueBit comes into the picture. We're bringing computation onto the blockchain, and in terms of privacy, I guess we've sort of made a trade-off. We've traded in privacy of big data in exchange for these other properties, which I call immutability, equality, maybe democracy. So that's sort of the new world that we're living in here. And the other thing you think about when you talk about big data is communication, right? The internet. There's some way that you have of communicating between the different parties that are involved in the network. And TrueBit is also involved in this piece of the puzzle as well. The original inspiration for TrueBit was the Doge Ethereum bridge, right? That's supposed to be a bridge between Dogecoin and Ethereum, where you can sort of burn your Dogecoin unlock them on the Ethereum side, run them in a smart contract, and then burn unlock, and voila, you have your Doge back. So that's where we started. Now, let's also look at how does TrueBit fit into the big picture here of scalability, right? So you have there's a few main ideas, different ways that people have thought about scaling blockchains along the lines of between the big data model and the blockchain model. So one is called sharding, and that's where you have a bunch of transactions, you break them into little pieces and somehow split the work up among many different parties. A lot of them are using Byzantine consensus type methods. Of course, you could also see by where the icons are on this page, where sort of the action is versus, like, say, academic action. But I mean, storage is a piece. State channels, Raiden, this is used for like micropayments. So you can sort of do a lot of stuff off-chain and then occasionally send an update, which is more expensive, that goes onto the on-chain piece. And as I said, TrueBit is also involved in communication. So the proximities in these on the page here are sort of somewhat intentional. And but the main, I sort of classify TrueBit as an interactive verification protocol, right? So this is it means, well, I'll explain what interactive verification is in just a moment. But the problem that we're solving is large transactions, right? You have big, we don't assume that transactions that are coming in are small. We take them that are large computations, and some transactions you might not be able to break into smaller pieces if you're doing, some sort of deep processing or computation, okay? So let's start off. What's the problem that TrueBit is trying to solve? This goes back to the idea of the verifier's dilemma. But first, let's talk about where's the verifier's dilemma come from? What does it mean? What is a smart contract? Let's start there. So we quote right directly from ethereum.org. Ethereum is a decentralized platform that runs smart contracts, which are applications that run exactly as programmed without any possibility of downtime, censorship, fraud, or third-party interference. Okay, clear? So basically you have a bunch of users on the network that you can send not only data, but also tokens onto the network. Well, I guess they can interact with each other or also through smart contracts, right? So smart contract basically consists of a code and some place with some storage where you can store not only data, like memory, but you could also store money, like tokens. So that's the whole idea of crypto economics, that you can interact with both of these. And of course, the other piece of crypto economics is that it's governed in some sort of decentralized way, which a consensus via blockchain decides how the smart contract actually acts on these things. But clearly, I want to emphasize that these pieces are only small computations only. So you're limited in the amount of stuff that you can put into the smart contract by this, what we call the Ethereum's gas limit. So let's get the elephant out of the room. Why don't we just let's obliterate Ethereum's gas limit, right? So what is the gas limit? So Ethereum meters smart contract storage and compute resources with gas. So gas measures how much storage and compute in some sort of metric for how much resources you're taking on the network. And the gas limit is the maximum amount of gas that you can use per block. So it's per block, it's not per transaction. So it's very limited. So it's around 6.7 million. So here's the quiz. So why do we have the Ethereum gas limit? Which is the following reasons best explained. So option A, every miner must replicate every Ethereum computation. So option B, removing the gas limit would leave Ethereum vulnerable to denial of service attacks. Option C, the gas limit helps incentivize transaction verification. Option D, Vitalik Buterin secretly doesn't want Ethereum to scale. Well, I think we can quickly rule out option D because it's not a secret anymore. So of the remaining options, it turns out all of these things are true, but one of them is more true than others, and I'm going to try to argue that that's option C. So this is perhaps the least intuitive reason, but let's see what happens. What is life like without the gas limit? Okay, so in order to do this, let's just take one step back. How does the blockchain work? So you have miners that are on a network. They're racing to solve a hard computational problem. The first miner who successfully solves the problem broadcasts his answer to the network. Then the next step, the miner appends a block of new transactions to the blockchain and receives a block reward, and the race begins again on top of this new block. So in this way, you get more and more transactions over time. They stay on there forever, and the blockchain gets longer and longer. So the security assumption that goes back to the very beginning of Satoshi Nakamoto, he said that more than half of the miners faithfully follow this blockchain extension protocol, regardless of financial incentives to do otherwise. So really, does this assumption reflect reality? And I mean, we've sort of seen people deviate from Bitcoin protocol from the very beginning. I mean, mining pools were not designed into the original protocol. So it's a bit of a rhetorical question, but in what way are people rational? So let's take a look of what happened. If some of you may remember back on July 4th, 2015, there was a fork. There was a fork on Bitcoin, and some of the miners were generating invalid blocks. In fact, Bitcoin.org still reads, roughly half of the network hash rate was mining without fully validating blocks. This is, they call it SPV mining, simplified payment verification. So they basically, there was an upgrade on the protocol, and there were some people, not to get into too much of the details, but they basically weren't validating the blocks. And it was a serious event. The July 4th block was 6 blocks long, which is a standard confirmation length. So some people who had confirmed transactions on Bitcoin had them wiped out. And July 5th, the same thing happened again the next day, but it was only 3 blocks long. So this is sort of where I myself came into the picture here. We had said a paper, saying like, look, there's this verifier's dilemma. It's an issue, and CCS said that's just a theoretical attack. It's never going to happen. But here, of course, it did happen, and they changed their mind, and we had a paper in CCS. So the question is, why did mining pools fail to validate? So sort of, why would you skip? So let's consider the world without the gas limit, right? So you have you have someone here who's bringing in a heavy transaction onto the network, right? So it's pretty heavy and it's subsidized. So he's included some sort of massive transaction fee. So of course, a miner will show up and say, sure, I'll include that. He's happy with the transaction fee. But the other miners on the network get totally confused. They don't even know what to do. So the question is, why are they so confused, right? So let me see if I can make us less confused about their confusion. So the verifier's dilemma. So what is the verifier's dilemma? The dilemma is, in case a heavy transaction falls on the network, what should a rational miner do? So option one, or rationale one perhaps, skipping verification affords an advantage in the mining race. So this is an observation. So this means you should skip the verification, because if you get a head start on the next block, you can earn more money, right? So or mine more blocks. Option two, or observation two, is that mining on the wrong chain means that other miners will ignore a found block, right? So if everybody, so this means you should do the verification, because if you mine a wrong block, then you don't. If you're mining on the wrong chain, you don't actually in the long run get paid for your work. So that's also bad. So you have a reason to skip the verification. You also have a reason to do the verification. And so it's clearly rationality doesn't help you decide what to do. So basically miners want to do whatever other miners are doing. So they're trying to reach some sort of equilibrium. Now, I mean, before I go on, I like to just make one observation, which is that it's not, there is another solution to this problem. So consider the following two strategies that both result in Nash equilibrium. The first one is that everybody mines on the longest chain, which is the standard assumption for Nakamoto consensus. The other one is everyone mine on the same chain as Ronen-Kirsch. Now, clearly, each of these results in a Nash equilibrium. The second one easily resolves the verifier's dilemma. Now, there's no ambiguity about where you should mine, but it's not so interesting, right? So it's really the clever choice of, number one, the convention that makes consensus decentralized and makes the blockchain work. So TrueBit also relies on a special convention, which is that honest buyers choose their tasks at random. And I'm going to say a little bit about how the protocol works now, so that you can maybe try to imagine how this convention sort of fits into the picture, and why a convention is really so powerful tool in the space of crypto economics as you're designing your own protocols. Okay, so dispute resolution. So this is the heart of our TrueBit. Well, first, what is TrueBit? Let's not get ahead of ourselves. The verifier's dilemma is something which prevents smart contracts from running for more than a fraction of a second. That's a fraction. Pardon. TrueBit is giving Ethereum a computational boost. We want to make smart contracts run not just for a fraction of a second, but like your MacBook, right? So it's a normal, fulfilling the vision of the world computer, if you will. So what are our goals for the protocol, or actually the properties that it's achieving? One is that anyone can offer a reward for performing a computational task. Anyone can solve a task in exchange for a reward. And most importantly, the protocol guarantees correctness of the solutions. So we don't want to just compute stuff, we also want to get the right answer. And here when I say the word anyone, I mean we're including smart contracts and any pseudonymous address that might be on the network, okay? And we achieve these properties based on two assumptions. One is that smart contracts compute correctly. This is just an empirical observation. And the other one is that agents are rational. They participate in maximized rewards. So if there's a mining task to be done and there's a reward for doing it, people will show up. And if there are ways that they can do to get more money, they'll do that too. So those are basically our assumptions for the network. And I would like to point out that formally, TrueBit itself is an Ethereum smart contract. So you can think of it that way. Okay, and in order to explain the protocol, I just want to review quickly what Merkle tree is. So this is just a tree structure that is going to be handy for this discussion, in which every child is the hash of its parents, okay? That's it. And this allows you to force some sort of commitment at the root, right? I mean, if you say the root here, then that means it's hard to fake the things that are above it retroactively. So TrueBit is a unanimous consensus protocol. So anyone in TrueBit can challenge a computation by what we said, taking it to court, right? So, and who lives in this court? Well, it's the judges. The judges are the Ethereum miners, right? So we assume that the judges they're always correct, but they have limited computational bandwidth. Okay, so how does it work? So you have a solver who comes in and says, I did this computation, and a challenger who comes back and says, no, you're wrong. And of course, I say, let's play a verification game. He doesn't have a choice. He has to, he's taken to court and he has to play this verification game. So anybody on the network the point is that anybody on the network can raise a challenge and bring it to the court. So how does the court work? The court works by pinpointing the disagreement, right? So we have to make it small enough that the judges, who are very limited computational power, can actually decide whether the computation was right or not. Okay, so your solver says, here are the Merkle roots of my computation. He listed them all out. And he says, do you agree at the halfway point, n over 2? Right? So clearly they agreed on the input because how the task is given there on the blockchain, and they don't agree on the output. So you go halfway through and says, did you agree here? And she says, no, I don't agree. Okay, so what about step n over 4? Says, yeah, I agree there. Okay, so now we're getting closer. And then finally, do you agree at step 3n over 8? So about halfway in between those two. Says no. Okay, now since there are only 8 steps, the miners can now just go and look inside of that, run that one particular step on chain, and see whether this computation was done correctly. And it's very important that the computational steps are identical across all the platforms, right? If everybody runs a different set of steps, then you have no way to actually do this last step. So having a uniform architecture is just absolutely critical for this, and that's one of the major technical developmental challenges for this project. Okay, so how does the final verdict work? And here we're looking back into the Turing machine model. Okay, so here is the last step where they agreed, and this was the adjacent step where they didn't agree. And if we undo the Merkle root, we see the information up here is telling us that we're in a Turing machine of state Q0, and the Q0 is seeing a 1 written on the tape, and apparently, according to the solver, it says that means he should write a 0, move to the left, and change to state Q1. That's what Turing machines do. They move heads left and write 0s and 1s. So if you don't know what a Turing machine is, that's fine. The important thing is that the judge actually ran the step himself and saw that he disagreed. You're actually changing to state Q2, and you're writing a 1 instead of a 0. So that means that this computation is bogus. So the challenge is justified, and this deposit is forfeited. And it's important to note that the deposits here that we're putting into TrueBit are a very significant amount of money. They're enough to run this whole computation. And there's also, if you go into the white paper, a list of basically 6 other criteria that the deposits have to be larger than this and this and this in order to make the incentive structure work. Okay, so I haven't talked about money yet, but let's see, how does the money come into the picture here, right? We have still one very big question. How do you ensure that the verification actually occurs? Like, we have this whole court, but how do you know anyone's actually going to use the court, right? I mean, this challengers are, maybe they don't want to show up. Of course they want to show up, because we're going to offer rewards for checking the computations. Okay, great. This incentivizes their participation, but it doesn't incentivize them to participate correctly, right? It says, I pay you to do the verification. You come back, he says, I did the verification, and then I says, now how do I know you did it right? Well, I go back and check it yourself. I said, well, I should have just done the computation myself in the first place. So that this doesn't work. So your second idea, or idea 3, I guess at this point, is to offer rewards. You offer rewards for finding bugs. Okay, so now you have the opposite problem. This incentivizes correctness, but it doesn't incentivize participation, especially when there are no bugs, right? Because no bugs you won't find any bugs. Nobody shows up to look for the bugs. So basically, the problem is the verifiers stop paying attention if they don't expect to receive rewards. Okay, so this brings us to our last scalability idea, which is the forced errors. So what we do is offer a bug bounty and provide expectation that bugs will actually exist. So this is TrueBit. So what we do is we occasionally, the protocol forces the solver to occasionally make a wrong answer. And that ensures that mistakes actually happen, so people are there to look for them and they can actually be incentivized properly. Okay, so, and of course, we want these random errors occur unpredictably and not every time, but on the times when you don't have a forced error, then the solver still thinks the verifiers are checking, so this means that he's still going to give the right answer. Okay, so ideally you're never going to use the court system because everybody always gives the right answer when there's not a forced error, so the whole thing is supposed to work. So that is, in a nutshell, is how this system works. And I think we can sum this up with a picture. Very interestingly, Simon de Rouviere came up with this picture for TrueBit even before we had the incentive layer of TrueBit back in, I guess, sometime in mid 2016. And this is a picture, he called it the Panopticomputer, named after, of course, Bentham Foucault's Panopticon, or Panopticism, depending if you, it's actually, so this idea of a Panopticon has taken physical manifestation in the state penitentiary in Joliet, Illinois, and also the Presidio Modelo in Isla de Pinos in Cuba. And what you see here is a tower in the middle. It's a prison. It's a prison. So all the prisoners are around on the outside. In the middle, there's a tower. It's a watchtower monitoring the prisoners with really bright light. So the prisoners can't see where the person standing in the middle, they can't tell what he's looking at, right, in the tower. So because they can't tell who he's looking at, out of fear that he's actually looking at them, they behave correctly. And as you see in the windows here, there's a lot of open space. So you don't have to lock up. It's not a high security prison. Everybody just behaves well. So and it can be done completely anonymously. As Michael Foucault wrote in his book, we have seen that anyone may come and exercise in the central tower the functions of surveillance. So this is a beautiful summary of how this protocol works. We can go into the details. You can check out their paper there are lots of, as we said, the devil is in the details, and I don't want to say the devil's in our paper. The details are in our paper. So you can check it out. I just wanted to sort of give, in the last few minutes of this presentation, talk about some of our development work. So WebAssembly is we've moved to a WebAssembly architecture. There's sort of, I step back here. We need an architecture in which a single computation step can run inside of the Ethereum gas limit, and it has to fit inside of it in a single Ethereum transaction. So WebAssembly gets us close to a sort of simple architecture, but it doesn't get us quite all the way there, so we have to still break it down a little bit further. And fortunately, since the time we started this project, there's been a lot more contributions and testing by Apple, Google, Microsoft, Mozilla. So WebAssembly is being used by other projects as well, like eWasm, Dfinity, Parady's also using WASM, so it's becoming very useful for the community, partly because WebAssembly is supposed to run in everybody's web browser, so it's also can run across blockchains in a uniform way, so everybody's running the same thing. So here's in a picture how our system looks. So the pipeline is thus. So when I say TVM, I call it the TrueBit virtual machine. It's this part that's sort of dark green on the side here. It's the off-chain interpreter piece that creates the list of computation stub steps, and the on-chain stepper, which is what the piece of the work that the judges are doing. Okay, so you have a piece of C code that you want to run, and somebody wants to run it. It's either a smart contract or one of these pseudonymous parties, and they kick this into this program called Mscripton, which we've worked into the TrueBit virtual machine off-chain piece, and that generates C code, transforms it into this WebAssembly, which is then created into the list of steps, like we had in the you create a list of steps for the computation. Okay, and then those are, of course, available for the judge to run it. The WASM task is also sent into the incentive layer, because that's how we generate the task. And then the incentives are all there to sort of make sure that the things work correctly. And there are some details here. For example, we have a jackpot repository, which is a bunch of money you put in to make sure the incentives are going to work correctly. We've had a lot of contributions from the community in terms of just the protocol level over the last few years. So updates coming soon in the white paper. A lot of projects are interested in, there are a lot of different ways you can use this system. We are ourselves have been focused on this building the Doge Ethereum bridge, which is we see that will become a reality soon, and so we're happy to give that back to the community, which people have been looking for that since the beginning of 2016. Anyway. We are, just to wrap it up, we have a project website, and we do now have a Reddit, Medium, GitHub, Twitter. So welcome everyone to please follow us along, contribute to our code, and generally engage with our project. So thanks very much.
Thank you, Jason. Any questions?
Hi. I just wanted to ask about your work with LivePeer. I noticed on your website that you guys have some projects you're working on with LivePeer in relation to, I think, scalability. Could you talk a little bit about that?
Sure. The LivePeer project is doing what they call decentralized live streaming video. So it should be anyone can broadcast a video, anyone can watch a video, and you're either paying to send or receive the video. And the place where TrueBit comes into the picture is in the transcoding process. So you want to also create this video into many different codec formats. You want to do it in different streaming resolutions. And that's an expensive process, especially to do in real time. So as I said, if you're trying to stream the Super Bowl, you don't want to end up watching Barney and Friends. So occasionally, TrueBit wants to make sure that you did the transcoding correctly, right? So the idea is that basically the way they have it set up is that we sample some of the transcoding gets kicked out to TrueBit, and if it's being done correctly, because TrueBit actually, you treat the TrueBit as an oracle that always computes correctly, then the person doing the transcoding should get rewarded for doing that.
Thank you.
Yep.
Any other question? No? Okay. Thank you.
Thanks.